Good morning, good afternoon, good evening, good night. Welcome to our seminar. Today we have a pleasure to have as our guest Professor Andrea Solotar from the University of Buenos Aires. She will speak on a subcap duality in Koszul calculus.
Okay.
We can start. Okay.
Gracias, obrigados. Thank you. And I'm sorry I cannot speak in Portuguese, but well, okay. So let me start. What I will explain is joint work with Roland Berger from Saint-Étienne. And it's all about a cohomology theory that we have been considering for a few years now. And it's called Koszul Comology. And well, you know, or you have, you know something about maybe Koszul algebras or n-Koszul algebras. This is a theory that is interesting when the algebra is not Koszul. And because if not, it's like a Koszul cohomology. Anomology, and so I will try to explain what is about Koszul algebras, Koszul cohomology, and some questions that we have and some things that we know. So it's a very recent thing, and so there are lots of things that we don't know, but well, we know some things. Okay, so let me start. Talking about Koszul algebras. For me, K, I will not say it again, it will always be a field. And well, most of you know Koszul algebras, in particular Eduardo. And Koszul algebras are homogeneous algebras, and they have been defined by Preedy in 1970. And well, in fact, they are called Koszul algebras because Preedy was following Koszul's method to compute the homology and the cohomology of the enveloping algebra of a Lie algebra. Okay, so you may think that, well, the enveloping algebra of a Lie algebra is an associative algebra, of course, but it's not homogeneous in general because there is a linear part. Okay. So this is not the case that we are going to treat, but if you are interested in how to extend this Koszul theory to non-homogeneous algebra, let's say when the difference is a linear part, it's very well explained in a book by Jean-Louis Laudet and Bruno Valette, Koszul operas, I think is the title. Okay, well, but the thing is that the method used by Koszul to compute to give a resolution inspired Preedy. Okay. So for us, A is going to be a quotient of a tensor algebra on a vector space B, which will be in general finite dimensional. It's necessary for some conditions. And it is divided by the ideal generated by a subspace R. And the subspace R is contained in the square, let's say the square tensor product of B over K, B tensor B. So A is going to be positively graded. It will inherit the grading from the tensor algebra, where the elements in B are in degree 1. And in particular, A0 is the homogeneous component in degree 0 is going to be K, and the component in degree 1 is going to be the vector space B, and this will generate A as a K algebra. Okay? So Yuri Manin considered the category of quadratic algebras, and there he defined three operations or three operations, let's say. One of them that is important for me today is a contravariant endofunctor of the category, and is the functor sending the algebra A, the quadratic algebra A, to A shriek. What is A shriek? It is another quadratic algebra that is the quotient of the dual vector of the tensor algebra of the dual vector space of B divided by the ideal generated by the orthogonal of the subspace R. Okay, and this functor leads to what is called the Koszul complex. Okay, so this is a theorem and a definition because, well, you can take one of these properties as the definition of a Koszul algebra and then prove that all the conditions are equivalent. Okay, so here we'll say that A is Koszul algebra if and only if the following equivalent conditions hold. So the first condition deals with the Koszul complex. The Koszul complex, I will talk about it in detail afterwards, is a complex that one constructs when looking for resolution, for example, of K as a algebra, as a module, and we ask it to be acyclic in positive degrees, meaning that the homology in degree 0 is K, and the homology in all other degrees, the positive degrees, is 0. Okay. An equivalent condition is to consider the X algebra and to ask the X algebra with the Yoneda product to be generated in degrees 0 and 1 as an algebra. Okay. This is also equivalent to the X algebra, which is a graded commutative algebra, to be naturally isomorphic to this algebra A shriek, which is the one defined by Manning, and it is a graded algebra too. Okay, and then another equivalent condition is to ask the E model K, as I said before, to have what is called a linear minimal resolution by free A models. What I mean by linear is that you will have a resolutions where all the components are going to be free A models, and all the differentials are going to be linear, meaning that you can write them like matrices. Okay, you're going to from an A power n to an A power m by a matrix, and by a matrix. Okay, and then an interesting thing to remark is that the algebra A is Koszul. You can verify either of this condition, if and only if its Koszul dual, A shriek, is a Koszul algebra too. Okay, so what about the Koszul dual and some easy examples? Okay, so let us consider start considering the polynomial algebra in two variables. Here you have you know that if you have completed it once at least, it has the Koszul resolution is finite. It's a short one. There are only 3 terms, and if you look at the dual, the Koszul dual, what is it? Well, it is the exterior algebra in two variables. Okay. Another example, let's say polynomial example, is to take what is called the algebra of dual numbers, K of x, one variable, divided by the ideal generated by x squared. So here you have a commutative algebra, and you look at the Koszul dual, and it is the tensor algebra in one variable that I call capital X. And if you look at them, well, what happens? The Koszul dual is free, but what is called a free algebra, but the algebra A in this last example is what is called non-smooth, meaning that the minimal resolution has infinite length, or non-smooth in the geometric from the geometric point of view too. Okay, so there is a kind of duality between the length of the things. But in particular, the last example shows that the Koszul complex may be infinite. Okay, you're going to have this infinite minimal resolution. Okay, and in fact, there is a kind of duality. I'm going to say duality several times today, being between the fact of A being Koszul and of finite global dimension, with A shriek being finite dimensional as a vector space. Okay, fine. Okay, so just a minute. Okay, so for example, in this last one, let me change. In this last one, we have an algebra which is not of finite global dimension, and A shriek is of infinite dimensional as a vector space. Okay. So what happens when A is Koszul? When A is Koszul, the situation is very nice if you want to compute some kind of homology or cohomology, because you have the Koszul complex, and the Koszul complex provides what is called a minimal resolution of K as an A model. And from this resolution, one can also obtain a minimal resolution of the algebra A considered as an A bimodule. And this resolution that you obtain may be, of course, used to compute Koszul, let's say, cohomology. Okay. What happens if A is not Koszul? Okay. If A is not a Koszul algebra, then you still have the Koszul complex, but this complex is not going to be a resolution because it's not going to be acyclic in positive degrees. And, well, you cannot use it to compute Koszul homology, but you still have a complex. Okay? So let me give an example of a non-Koszul algebra, a quadratic algebra. So consider this quotient. This is the quotient of a non-commutative algebra in two variables, x and y, and it is divided by an ideal generated by two elements, the product yx and the product y squared minus xy. Okay. So suppose that you want to compute the Koszul complex. Let's say the Koszul complex is going to be in this case like this. Now you have A tensor A and the multiplication to A. Then you have three other components. Here you have the vector space B, which is generated by the variables x and y. Then you have something in the next degree, in degree 2, that corresponds to the relation. Okay, this is a vector space of dimension 2, W2, and it has then two generators. The first one corresponds to the first relation, and the second one corresponds to this second relation. Okay, and there are some differentials that we know how to compute them. And in the following term, here the third term, there is a vector space in the middle, which is in this case of dimension 1, and it corresponds in some way to the superpositions between this, the leading term of one relation and the leading term of the other relation. When I say leading term, there is an order between the variables. Okay, so in this case, the Koszul complex has in degree 3 this generator W, which corresponds to this element that is going to belong to the intersection of the subspace R with B on the left and on the right. Okay, and this is how you are going to continue constructing the Koszul complex, but here there is a 0 afterwards. Okay, so this algebra is not Koszul because this complex is not exact. And for example, I'm going to show you an element which belongs to the kernel of D1 but does not belong to the image of D2, and the element is this one. And maybe the element means nothing to most of you, but if you look at the element, you see that you have here the relations appearing R2 and R1 that are quadratic, and the other things that appear in each terms are of degree 2, x, y, y here and here, etc. Okay? So the fact of these things being quadratic, being of degree 2, is in some way the reason why they are not in the image, okay? Because these differentials are linear, okay? So you just get things in the image of this differential that has, except for the r's, degree 1 somewhere, okay? So, but this is just an example of a non-Koszul algebra. There are lots of non-Koszul algebras, okay? But as I was saying, we still have a complex, and so we can apply to this complex the functors either tensoring by an A by module M. This is enveloping algebra, A tensor A op, or taking the home functor. Okay, in the same way that you do when you are trying to compute Koszul homology and cohomology. Okay, but of course here we are going to get different things. In case A is a Koszul algebra, we obtain the Koszul homology and cohomology, but if not, we get some new invariants. This is the reason why I was saying at the beginning that this is a theory that is interesting when the algebra is not Koszul. So in the previous examples, the example of non-Koszul algebras, we obtained that the cohomology in degrees 0, 1, and 2 are isomorphic to the respective Koszul spaces. But for example, in degree 3, this thing that is what I call and will define the Koszul cohomology in degree 3 is one-dimensional, but the Koszul cohomology is two-dimensional. And for degrees greater or equal to 4, the Koszul cohomology will be 0, but this is not the case for the Koszul cohomology. Okay, so maybe you have thought about Calabi-Yau or di-Calabi-Yau algebras, and you know that for Calabi-Yau algebras there is a duality between Koszul homology and cohomology, a kind of Poincaré duality, okay? And for example, this duality cannot be true when the algebra has infinite global dimension, okay? But there may be a part of this duality, sometimes exists, and we will see it later, that is, let's say, that the Koszul cohomology detects kind of duality that the Koszul homology does not. Okay? So we are going to speak about dualities again later. So let me talk about in more detail about the Koszul cohomology and homology. 3 years ago, we defined this theory with Roland Barger and Thierry Lambre in a paper in Glasgow Mathematical Journal. So we defined this theory, and so we got a cohomology and some more structures, some products, which is a cup product in cohomology and a cut product that is the action of cohomology on homology. And we got what we call a Koszul calculus. So a Koszul calculus is something that exists in Koszul cohomology. Calculus exists in Koszul cohomology and homology. I mean, cup product, cup action on homology, and also what is called a Tamarkin-Zigan calculus. So let's look for a minute to Koszul theory. So as I was saying, in Koszul cohomology, you have a cup product you have a Gerstenhaber bracket in cohomology, and you have an action of cohomology or homology given by the cap product, okay? And you also have a map, an operator, capital B, that goes from the Koszul homology to the Koszul homology in the same degree plus 1, and the square of this operator is 0. So in this way, you get a differential, and you get something that in the non-commutative case, when A is a non-commutative algebra, plays the role of the RAM, a kind of the RAM cohomology, okay? So in particular, you can define the higher Koszul homology spaces, taking the homology with respect to this operator, okay? And another feature, another important thing in Koszul cohomology or homology is that the differential that you use to compute the Koszul cohomology, when you use the power solution, can be obtained as the Gerstenhaber bracket with the multiplication. The multiplication is a 2 cocycle, okay? So let me say here that, let me say now, that the Koszul cohomology that we are working on does not have a Gerstenhaber bracket, okay? And does not have a Gerstenhaber bracket because we cannot perform the needed compositions. So what do we have in the Koszul cohomology theory? We have a cap product that I'm going to define later. And we have an action on Koszul homology given by a cap product. And also in characteristic 0, we are able to construct a differential. Here, I'm sorry, it's a typo. It should say Koszul HK from HK of A to HK star plus 1 of A. And this differential, the square of this differential is again 0. And also the differential small, let's say, bk of the complex that we use to compute Koszul cohomology is not the Gerstenhaber bracket with something, but it is the cap bracket, the commutator with an element, a particular element that we call EA, which is the fundamental class. And this is an element which is the class of a 1 cocycle that appears from the Eulerian derivation corresponding to the usual grading. That is, all the variables, all the elements of B are in degree 1. Okay. So we managed to have this kind of analog to the RAM cohomology again here. Okay. If you have questions, please interrupt me. Okay. Fine. So there is a duality theorem in Koszul cohomology, like we proved it in that paper in 2017, and it's like this. You have a finite dimensional vector space, you have a quadratic algebra, and then, sorry, you have A freak, the Koszul dual of A. And you know that for Koszul cohomology, when the algebra is Koszul, there is a duality between the cohomology of A and the cohomology of A freak. Well, the same happens here for the Koszul dual in the Koszul cohomology. And we have an isomorphism of, they are bigraded unital associative algebras, which is the Koszul cohomology of, the Koszul cohomology of A with the cap product is isomorphic to the Koszul cohomology of A freak with the cap product. And there is a tilde here and here, because the tilde means that there is a difference of a sign when you compute the cohomology. But personally, I have tried to use this isomorphism in Koszul cohomology to compute things, to compute some cohomologies that I didn't know. And it's not quite direct, let's say, because there is a change, an interchange in the degrees. So you have a graded algebra A. This induces a grading on the complex, on the cohomology complex. Okay, and so you have an n times n grading because you have the cohomological degree, and you have the degree coming from the degree of from the grading of the algebra. Okay, and this isomorphism interchanges both degrees, let's say. Okay, so the isomorphism is like this for Koszul in the Koszul case, and in the non-Koszul case, or in the Koszul case too, is like this. Okay, there is just a change of sign. Great. So before continuing, let's talk a little bit about Koszul for non-quadratic algebras, because, well, there are a lot of homogeneous algebras which are not Koszul, and there are, we have seen different definitions, equivalent definitions of Koszulity in the quadratic case, and if you look at them, there are some of these definitions of these equivalent conditions that can be easily generalized to a non-quadratic case, and other ones that cannot be generalized. Okay, so it's very easy to prove that if you have a quadratic algebra which is Koszul, then if you have an homogeneous algebra which is Koszul, then this algebra must be quadratic. Okay, but we want more than quadratic algebras. Okay, so how to generalize this notion when you have a homogeneous algebra, which is a quotient of a tensor algebra divided by homogeneous relations, not in degree 2, but in degree n. So we are fixing capital N here, okay? So there is a notion, there is a generalization by Roland Berger. He considers a graded algebra. As always, A0 is K, and the algebra A as an algebra is generated by the degree 0 and the degree 1, and there exists a projective resolution such that the n projective module of the resolution is generated in a particular degree that we call nu of n, and nu is a function from the natural numbers to the natural numbers that is defined like this. Okay, it's something for the even natural numbers and something for some different thing for the odd ones. Okay, and let's say the nth projective module of the resolution, it's like this. Okay, so it's free as a bimodule. I'm talking about resolutions of bimodule, A as a bimodule. So you have A on both sides, and in the middle you have, well, this vector space. Okay, so in the case of the quadratic algebra in degree 3, I had here B tensor R intersection with R tensor B. Okay, so it was a particular case of this. Okay, but then there was a more general definition by Green, Eduardo Marcos, Roberto Martinez Villa, and Pu Zhang. So they allowed A0, they were thinking about quotients of past algebras, Hilbert algebras. So they allowed A0 not to be just K, but semi-simple, K, many times K. And then they defined that the algebra was n Koszul if the X algebra is generated in degrees 0, 1, this was for n equal 2, and 2. And this is the new thing here. Okay. So we have the definition of n Koszul algebra. In the paper I mentioned with Berger and Lambre, we defined the Koszul cohomology for quadratic algebras, okay? But we want it now in a more general setting. So let's say why, for example, because n-Koszulity is something that appears in very, very different settings, well, in representation theory, there is the problem of Calabi-Yau algebras, as I mentioned before. You have the Young-Mills algebras, which are 3 Koszul. There is a Poincaré duality in Hawkes homology. Also, there are relations with what are called A-infinity algebras. There are problems in quiver algebras also that are interesting. And all of these can be done in the setting of operands too, okay? So we are interested in these generalizations. And so Berger extended what we call the Koszul calculus for n Koszul algebras, so n greater or equal to 2, and this was last year in Journal of Algebra. And then, together with Rachel Taillefer, this year in the Journal of the London Mathematical Society, they also consider the case where H0 is a semi-simple K-algebra, and they define the Koszul cohomology in that case. Okay, why they were interested in defining it for H0 semi-simple? Well, because they were trying to compute, to describe the Koszul calculus for pre-projective quiver algebras. Okay, I'm not going to give the definition here of pre-projective quiver algebras. It is some kind of quotient of a path algebra. Just to explain it briefly, very briefly, you start with a graph, okay, with a graph, and then you have in the graph you have some arrows and you have some vertices. You have a directed graph, and then you add for each arrow an arrow in the other sense, okay, which you can you kind of add one arrow for each arrow you have, okay, and then there are some relations interchange using both types of arrows, okay, and in particular, when you start with a Dinkin diagram, they are very interesting pre-projective quiver algebras, and so they prove that if you have a pre-projective algebra and the diagram, the graph you consider is different from A1 and A2, the linking diagrams, then the Koszul cohomology of A with coefficients in A tensor A up in degree P is isomorphic to the homology in degree 2 minus P of the same thing. So there is a kind of duality here, okay? And this is for all P between 0 and 2. And moreover, they prove that in degree 1, both of them are 1. In degree 2 of the cohomology, you have A, and in degree 0 of the cohomology, you have something different from 0. When? Well, when the graph is a Dinkin diagram of type A, D, or E, okay? And so, inspired on this fact, on this duality, they define a new notion that they call the Causal Complex Calabi-Yau of dimension n, and this is so an algebra is Causal complex Calabi-Yau of dimension n if the Causal complex has length n and the derived functor, well, of this is isomorphic to the Causal complex shifted, okay? And this is an isomorphism in the bounded derived category of A bimodules. Okay, so they proved this. And they also proved that if you have an algebra A, which is complex, Koszul complex Calabi-Yau of dimension n, you will have this duality for any bimodule M. Okay, and moreover, this is they know exactly from where this duality appears, and it comes from a cap product with an element which is the fundamental class, that is the one that I have mentioned before. Okay, so these algebras, these pre-projective quiver algebras will never be Calabi-Yau in the usual sense of Calabi-Yau. But there is another property of being Calabi-Yau Frobenius that has been recently defined by Eu and Travis Schedler. And they also proved that pre-projective quiver algebras have this property. And so it's kind of, the situation is like if you are recovering in Koszul cohomology a duality that was not there for Koszul cohomology just because of the infinite global dimension. So let me mention that the Koszul cohomology of pre-projective quiver algebras of type ADE is periodic of period 6. Okay, so you never have a kind of duality like this. Okay. So now our context, the context we have in this preprint. This is I'm talking about a preprint that we have we put in archive this year. Okay. So we are going to consider the situation with a 0 equal to k, okay, and we are going to have a vector space V and an integral greater or equal to 2 that we fix. So we have the tensor algebra. It has a grading coming by the weight, meaning that the elements of V are in weight 1. We fix a subspace, and then you take the quotient, and then it inherits the weight grading. So, in particular, the component, the homogeneous component in degree m is going to be this if you have not reached the degree n, the capital N, okay? So I'm going to give in a few moments a definition of a cup product, and one of our questions is if this cup product is or not graded commutative, like the cup product in Koszul cohomology. And similarly, if the cup action is or not graded symmetric, okay? And again, we know that this is the case for Koszul cohomology. In fact, there is no written proof of this, but okay. So the answer is, of course, yes, when the algebra is n Koszul. Why? Because Koszul cohomology coincides with Koszul cohomology, and our cup product coincides with the usual cup product, and it's known that it's graded commutative. And so, up to now, we are not able to prove that this cup product is graded commutative in full generality, but we have some situations where it is graded commutative. We do not have counterexamples. And we are able to prove that if it is graded commutative, then the action is graded symmetric. Okay. And in order to do this, we prove a theorem that is given by a commutative diagram like this. So it relates Koszul homology, the dual vector space of Koszul homology, with Koszul cohomology with coefficients in the dual. Okay, this is quite general. This is the bracket, this is the commutator with a sign. And this expresses the symmetry of the cup actions, okay? And we prove that we have vertical arrows which are isomorphisms, okay? So from this diagram, we are able to prove that if the Koszul cup product is graded commutative, then the action is graded symmetric, okay? So while trying to prove the graded commutativity of our cup product, we considered, well, different cases, and then we tried a new approach. We have not been able to prove everything, but well, I think that this is interesting anyway. So going to definitions, just detailed definitions, okay, trying to tell you about it. So these are the spaces that I have mentioned before, okay, these intersections. This is the thing that are going to be the base that are going to generate each term of the bimodal resolution as a bimodal, okay? And well, we fix W0 equal to K, and if we have not reached this degree, this is just B tens or P times, okay? And we are using the same function nu as before, okay? But well, now we have an N here. And so what is the Koszul complex? Well, the Koszul complex is a complex like this of 3 A bimodals, and in degree P, I have this thing, okay? And what happens with the differential? We need to give the differential. Well, the differential is quite different when you start from an odd degree than when you start from an even degree, okay? So in the odd degree, it is very nice. It is just, well, you keep the kind of first part of the Koszul differential and the last one. Okay, it's just two terms, very nice. The ugly thing comes for even degrees. Okay, so for even degrees, you have to keep a part in the middle that, well, fits into the Koszul complex you have. And this is because this function nu, okay, you have to make a kind of jumping degrees. And I'm just a just a remark on the notation, okay? Maybe I don't have monomials in the Koszul complex, but I'm just trying to avoid the sums here, okay? Defining monomials, but meaning that I take sums corresponding to the Koszul complex. And if you have ever computed resolutions of, let's say, the bar resolution or resolution, the minimal resolution of monomial algebras, okay, you can look at it and notice that it's very, that it resembles a lot the differentials in the minimal resolution of monomial algebras, okay, that are also different in the even and in the odd case, okay. So a remark is that in degree 0, you have always the homology is A, and in degree 1, you have always homology 0. It's exact. This complex is exact in degree 1. And in case you have big N equal to 2, the quadratic case, it is a subspace. The thing in the resolution is a subspace of A tensor P. Okay, and then the Koszul complex is a subcomplex of the bar resolution of A. But if you are in a case where you have N, which is greater or equal to 3, then there is no natural inclusion of this complex in the bar resolution. But since we have a graded algebra, in the category of graded A bimodals, A has always a minimal projective resolution that we call P star A, and the component in degree P, well, we denote it like this, and EP is a graded space, and we still call weight the degree, okay? So let us look at this in a closer way. So the components of this AP in degrees in weight less than nu of P are always 0. And the component of this exact weight contains the thing that appears in the Koszul complex, okay? So if you have any N, the Koszul complex can always be viewed as a graded subcomplex of the minimal resolution. And the algebra is n Koszul if and only if they are equal, okay? So in degree 0, both have K, in degree 1 both have B, in degree 2 they have R, the relations, and the component of weight nu of 3 in E3 is exactly what comes from the Koszul complex. Okay. So you have to keep the idea that you are inside the minimal resolution. But if you have a big N, let's say, and you look one step further, the component of this weight in A4 is not exactly W nu of 4. It may contain this thing strictly. And this not happen for n equal 2. Okay? So from all this discussion, one can prove that if you have the Koszul cohomology, anomology, and the Koszul ones, the Koszul cohomology has a surjective map into the Koszul cohomology in degree 2, just degree 2, while the Koszul cohomology has an injective map into the Koszul cohomology in degree 2. Okay. So let me talk a little bit about the products. This is a not very nice formula, but just to tell you how the products, the Koszul products, are defined, and it depends on whether the indices are both odd or not. Okay, so if they are not both odd, okay, this gives a formula for the new function. Then the cup product is very easy to define. It's just as the cup product. Okay, same formula. But if P and Q, the indices are both odd, and then you have a more complicated formula for nu of the sum, then in order to compute the Koszul cup product, well, you have a very, very horrible, let's say, formula. Okay. For the action for the cup product, there are also two cases that I'm not going to detail. The first one, when both of the indices are, when they are not both odd, it is easy, and when they are both odd, it is not so easy. Okay, more complicated. But there is an important fact about these products is that if you have Koszul cochains in this complex, then you have associativity relations. But it is important to notice that these associativity relations hold for n equal 2 for the quadratic case, but they are not true at the cochain level for n bigger than 2, okay? And however, they are true at the cohomology or anomology level, okay? So this fact, the thing of not having this associativity for the cochain level in degree greater than 2 makes things more complicated, as you will see. Okay, so some examples now. There is a fact that we can prove is that when you do the Koszul bracket is, I mean this one, no? With these signs, okay? So when you have that P, one of the degrees is either 0 or 1, for any beta of any degree, so with something of degree 1 or 0, the Koszul product, the Koszul cup product is always commutative, okay? This comes from the fact that, well, HK0 is the center, but what happens for degree 1? Well, for degree 1, the cocycles come from derivations. And so you can still do a computation to prove that this equality is true. Okay, I will get back to this. So if you have, for example, as a corollary, an algebra for which the Koszul cohomology is generated in degree 0 and 1, then of course you are going to have commutativity, graded commutativity of the cup product. Okay. Another case where the you know that you have commutativity of the cup product is, as I said before, for the n Koszul case, okay, since you know it for Koszul cohomology. Okay. More examples. I have mentioned at the beginning that this algebra is not Koszul, okay? So if you compute the Causal Complex, which is not so difficult, then one can prove that if you do a Causal cup product between things that are not both are not of degree 0, so you are in positive degrees, then all the possible cup products are 0. Okay. In particular, it is commutative, graded commutative. Okay, so you have an algebra here whose Koszul cohomology is not generated in degrees 0 and 1 as before, because there is a degree 2, but it is still graded commutative for the cup product. Okay. And in general, if you have an algebra and homogeneous such that the length of the Causal complex is at most 2, then you can prove that the cup product is graded commutative and the action is graded symmetric. Okay. Let me talk a little bit about what happens for monomial algebras defined by one relation, by a single monomial relation. So in this case, well, you have a vector space, you fix a basis, you have a monomial, and then you quotient by the ideal generated by this monomial. Well, in this case, you always have a graded commutativity, okay? So Berger proved it in a previous paper. What happens with the Causal complex? And well, it stops somewhere in degree n plus 1, except in one case, that is when the algebra is a power of one variable, when the monomial is a power of one variable. Okay, so in case the monomial is different from this one, the complex, you can prove that it has in fact length 2, and then we conclude. And if this is the case, then the algebra is n Koszul, and we can conclude. Okay. Just to mention that within the class of n-homogeneous algebras with a single monomial relation, one can describe which are the non-n Koszul algebras, and the non-n Koszul algebras are those coming from dividing by a monomial like this, where you have n, capital N, which is fixed. You take an m, you divide, you make the division by m, and you have the remainder here, and you ask not all these indices to be equal, okay? So these are the non-Koszul algebras in that framework. Okay, so the last part will be, well, what do we know about the graded commutativity in general? Well, we don't know a lot, but we have tried to look at the proof of the graded commutativity of the cup product in Koszul cohomology. And there is the original proof, and the original proof was given by Gerstenhaber, okay? And it was related with the appearance, with the first definition of the Gerstenhaber bracket, okay? So if you have computed the Gerstenhaber bracket, you make some compositions, you make a sum of compositions in one sense and in the reverse sense. And these compositions, well, you have to apply one of the cocycles and to get an element of A and then replace it in some part of the argument of the other cocycle, okay? The problem here is that you are not sure if you do this, that what you get is a Koszul, is an element of the Causal complex, okay? So you cannot do it, you don't have Gerstenhaber bracket. And not having Gerstenhaber bracket, you just have it when one of the elements, you just have a part when one of the elements is of degree 1, it's a one cocycle, And this is why the commutativity, we know that it works for the one cocycles, okay, that I mentioned before. But if not, you cannot do it. And so this kind of argument is not available. Okay, so you have to think about something else. Another proof of the graded commutativity of the cup product in Koszul homology is obtained by what is called the Ekman-Hilton argument. Okay, this is a more categorical proof, and the problem here is that this argument works for derived functors, and this is not what we have. We have defined the Koszul cohomology as the cohomology of a particular functor. Okay, so we cannot do this neither. So don't think about it. So we decided to develop another strategy. And the strategy, well, is we need to be next to Koszul cohomology, because there we know what happens with the cup products. So we prove that the Koszul cohomology is in fact isomorphic to what is called a Koszul hypercohomology. So let me explain this. So our idea is to divide the proof in two steps, okay? The first step is what I have just mentioned. The Koszul cohomology is isomorphic to a Koszul hypercohomology. And the second step is to show that this isomorphism of the first step sends the Koszul cup product here to a Koszul cup product. And the Koszul cup product, we know that it is graded commutative, and we are happy with it. Okay, so we succeeded proving the first step, and then I will tell you what are the problems with the second one. So the first step, in our context, in our setting, we proved that the Koszul cohomology of A with coefficients in an A bimodule M is isomorphic as a graded vector space to what is called the hyperhomology of the algebra A, hypercohomology of A, with coefficients in this. What is this? This is not a bimodule, this is a complex of bimodules, okay? They are bimodules because I have A here and not A tensor A up. Okay. In order to compute this, you need to compute a resolution in another category, in the category of complexes. You have, for example, what is called the Eilenberg-MacLane resolution. But, well, there are problems with that. Okay. So we have this isomorphism, but we still have, from this isomorphism, we can induce from the cup product, the Koszul cohomology cup product here, but we need to compare it with the usual Koszul cup product, okay? So the second step, this was the first step, and then the second step is what we have tried to do in this article, and so we have developed a lot of structures. It needs some what are called enriched structures in the category, and then we explicitly describe this enriched structure, and we need an extra hypothesis also in the case n equal 2 in order to be sure that we have the injective resolutions we need, okay? So we need to assume the existence of injective resolution in a certain category. And the certain category is the category that we had before, but enriched over this differential graded algebra that comes from the Causal Complex, the differential I mentioned, and the cup product. It is a differential graded algebra for n equal 2, but not for n greater than 2. Okay, it's just a weak differential graded algebra. There's a problem with associativity, as I mentioned in the beginning. But in the particular case, when it is associative, we can prove the following. We can prove that the isomorphism that we had in the previous proposition is not only an isomorphism of vector spaces, but an isomorphism with reflecting some more structure. Okay, that I'm not going to detail today. Okay. And so with the hypothesis on the existence of resolutions, we obtain that this Koszul cohomology and this Hochschild hypercohomology are isomorphic also as graded by models over the Koszul cohomology. Okay? So what would we need? Well, we would need to prove that this bimodal is symmetric, but this is the part that we have not been able to do yet, because we have not succeeded relating the action that we obtain with the cup product in Hochschild cohomology. But anyway, we think that it may be a way to prove the graded commutativity. Okay. This was for n equal 2. For n greater than 2, okay, Berger conjectures something about this A infinity that is not an associative algebra, but he thinks that it is, he conjectures that it is an A infinity algebra, and that we can extend all the structures to be A infinity by models, etc. And then, in that case, we would need the isomorphism to be an isomorphism of A infinity A tilde by models. Okay. And with all this, the proof will work for n greater than 2. Okay. So this is all I wanted to tell you. Thank you very much for your attention.
Thank you very much, Andrea. Thank you very much. Let's thank any questions, comments?
I have one question.
Okay,
Yeah.
please. Wow.
About the simplest example of non-Koszul algebra. But if it is not, Pridi has a theorem that each Poincaré-Birgit algebra is Koszul algebra.
Mm-hmm.
And so why we cannot apply this theorem to this simple example? I cannot understand this.
Okay. Well, there are several ways to prove that it is not a Koszul algebra. I have to think, because, yeah, you have a basis for this algebra.
I have the basis.
Yeah, you have the basis that is where 1x, y,
if
x
we suppose
times
that y is greater than x,
yeah,
then we have a basis.
Yeah, we have a basis, that is for sure. But if you could try to compute to use the criterion using the Hilbert series, the coefficients of the Hilbert series are not the good ones, and the resolution is not the good one. I don't know, yeah, why, which is the problem with the PBW basis, but I should look at it.
I have the impression that when you try to do the minimal projective resolution in degree 3, it fails to be.
Of course, in degree 3, it fails completely, because there are things that should be in the resolution in degree 3 and that are not there. And the problem is that, when you start constructing the resolution, you have this superposition of things, and you have relations that come from the relations that you have. For example, if you have x, y, x, or y, x, y, they are all 0. And this gives resolutions that you don't see them from the relations. This may be the problem. Thanks, Eduardo. Because there are relations that are deduced from the relations we have. So the basis that maybe you're thinking is not exactly the basis that you need. I think that everything in degree, not everything in degree 3, but x, y, x is 0. This is for sure. And then there is only one thing, only one monomial in degree 3 that is not 0. I don't remember which one exactly. I have it somewhere. But there is only one. Okay, and I think that this is what fails with the PBW basis. I'm trying to find it, but I don't think that I will find it now. Yeah, XXY,
Okay.
for example, is 0. Okay, this is the problem. And
The problem is,
remark
what
it,
is 0, 0, x, y, x?
for example, XXY is 0. Must be 0.
XXY is
You
0.
have, yeah, you have to add this relation,
Okay.
and this causes a problem.
Any more questions or comments, please?
Okay, thank you.
And let me see. You showed that the Koszul, for those examples, the Koszul complex, the Koszul homology is finite, yes?
In that example,
Yes.
yes, it's
So that is
stops in
another
degree
proof,
2.
because the Koszul homology is not, and they coincide when it's Koszul.
But it is not Koszul algebra.
Yes, the algebra is not Koszul, so there is
Yeah.
another proof that the algebra is not Koszul.
Yeah. How do we prove it? I computed it. I computed the whole homology and cohomology.
Yes.
I can tell you what it is. It is.
No, I'm saying that what you did is another proof that the algebra is not Koszul.
Yeah. But, well, it's just a computation. I don't call it a proof.
Yes, but it is.
Yeah. It's infinite dimensional in the cohomology, infinite dimensional in degree 0. Just a minute, I will tell you. One dimensional in degree 3. 2 dimensional in degree 1 and 2. That's it.
Yes.
No, sorry. 2 dimensional in degree 1 and 1 dimensional in degree 2 and infinite dimensional in degree 0, and that's all.
Yes.
Okay, more questions? Questions, comments? Okay, thank you. Thanks once more. Yeah, thank you very much.
Thank you for the invitation.
Okay.
Well, one question
Okay.
more
Yeah.
after all
One more
everything.
question. Okay.
But XXY is not 0.
Yes, it is. It must be the consequence of the relations.
You are sure? Okay, I will check.
Yeah.
Okay, thank you. In any
Because
case.
I can, if you send me an email, I can scan the computations
Okay,
and send them
okay.
to you. Okay.
Thank
Bye.
you, thank you.
Okay. So thank you, Andrea, very much. And
Thank you.
Announcements for the next Thursday, we will have a talk by Albert Solomonovich Schwartz from University of Davis of California. He will speak on some questions on Jordan algebras inspired by quantum theory. So see you, all of you, the next Thursday.
Bye.
Bye.
Okay.
Bye.
Thanks for participation. Okay. Till the next Thursday. Bye-bye.
Bye.